Hello, my name is Haree. My metric number is U2004887, and this is Optimization Techniques, SIN 2008. So for the first question, I was given a multivariate function, which is fxy equals to ax power 4 plus by power 4 plus cx square y square plus dxy. And I substitute the value of my four last digit metric number, which is 4, 8, 8, and 7, and I got this function over here. So the question asks us to find the optimal curvature values by utilizing the appropriate Hessian matrix. So the first step, as usual, is to find the gradient with respect to x and y separately. And the easiest way to find the stationary point is to let both x and y to be 0 respectively. And then I move on with the Hessian matrix. So to find the Hessian matrix, we need to know the second order derivative. So I computed for the x, for the y, and for the xy and yx. So the xy and yx, they have the same derivative, which is 32 xy plus 7. Once I put that into the Hessian matrix and substitute the value of 0, 0 for the x and y coordinates, I get the value negative 49, which is less than 0. And since the first order, which is fxx equals to 0, and the second order, which is determinant of Hessian matrix, which is less than 0, negative 49, this clearly indicates that the point xy 0, 0 is a saddle point. And moving on to question number 1b. So this question asks us to compute the value of the last four digits first. So therefore, after I computed the last four digit, 4 plus 8 plus 8 plus 7, I got 27. And therefore, I had to do the fourth method, which is the quasi-Newton BFGS method. So the first step in the quasi-Newton method is to find the gradient as usual. So I got the gradient, which is 16x cubed plus 16xy squared plus 7y, and 32y cubed plus 16x squared y plus 7x. And from there on, I just assume that my x naught, y naught to be 0.5 and 0.5 to start off with. And then the b naught inverse, I use it same as in the lecture notes, which is the identity matrix 1, 0, 0, and 1. And the step size I use the same in the lecture notes, which is 0.2. So I calculated the gradient at x naught after substituting the value of 0.5 and 0.5 into this equation up here, and I got 7.5 and 9.5. And then for step 2, I just mentioned it again for the alpha and the b naught inverse. And then on step 3, I calculated the x1 and y1, and this marks the first iteration. So my x1 and y1 are negative 1 and negative 1.4. And then I calculated the s naught value using the formula, the latest xy minus the previous x and y. So I got this value. And then I calculated the capital Y naught using the current gradient minus the previous gradient. And then I got the current gradient. And then therefore, after I got current gradient, I substituted into the function. I got the Y naught value. And for step number 5, I calculated all of these complicated calculations involving S and Y and its transposes. All of this calculation is actually to find the B1 inverse, which I have it over here. And then I continued to the second iteration and calculated the x2 and y2 values. And I got the x2 and y2 value to be negative 1.16 and negative 0.83. And then I move on with the calculation of S1, which is the latest x and y minus the previous x and y. And then I calculated the current gradient of x2, y2. And therefore, that allows me to go to step number 4 to calculate the y1 value, which is the current gradient minus the previous gradient. And therefore, to calculate the B2 inverse, I had to calculate again the complicated S and Y transpose multiplications. And therefore, I got the B2 inverse to be 0.684047, negative 0.127520, negative 0.127520, and 0.031185. And I moved on with iteration number 3 to calculate the x3 and y3 values. On substituting the entries that we already have, I got the x3, y3 to be 3.699948 and negative 1.670530. And I calculate again for the S2 and Y2. And moving on, I calculate the multiplication of S2, Y transposes, and Y and S transposes, all of sorts, to get the B3 inverse. And I didn't stop there. I just went again for iteration 4 to calculate the X4 and Y4. And I calculated the S3, the Y3, and then all these calculations to get the B4 inverse, which we have it over here. And as the last iteration, it's iteration number 5. I calculated x5 and y5. So I got this value over here for x5 and y5. And I calculated s4 and y4 to go on to calculate the B5 inverse, which is the final one over here. And to check my answer, I actually use C++ code. So this is the code that I have over here. So for the code, as you can see, I use the include IO stream to allow the input and output operator, include IO manip to have the maths formulas, and I also have CMAT to have the precision for the decimal places. So I use the namespace std, and then I set the iteration to be 20. I set it to be a constant value, and also the alpha I set it to be a constant value also of 0.2. The first function is to calculate the gradient. So this is the gradient of x, and this is the gradient of y. And this function void print matrix actually prints the x and y iterations. And inside the main function, we have all the formulas. So if I just click run over here, you can see the iteration 1 value would be -1 and 1.4. Iteration 2 would be -1.16 and -0.8297. And moving on to iteration 5, we have the values to be 2.679955 and -1.306773. Comparing to my answer, 2.67 and -1.3, I got 2.67 also and -1.3. And my answer is almost close to the one in the Excel. And we keep going to the last iteration, iteration 20, we get the x and y value to be 1.03 and -0.62. And if we compare it with our calculation over here, it is quite far off because this method converges very slowly. And that marks the end of question number 1b. And I move to question number 2. So for question number 2, I've been given another multivariate function. But in this case, the numbers is dx cubed plus cy cubed plus bx square y plus ax y square. And upon substituting my last 4 digits of my matrix number, I get this function over here. And to see which method that I use to solve, I have to compute the total 4 digits of my last metric number. So I got 27 to be sharp, 4 plus 8 plus 8 plus 7. So I had to do the conjugate gradient descent method. Before that, I updated the constraint values after substituting the values. So I got my constraints to be x square and y square less than equals 15, x plus y more than equals 8, and x and y both to be non-negative. So the first step is to lay out iterations very clearly. And because I'm using the conjugate gradient descent method together with the penalty function, I have to make sure that the equation, the inequality must be less than equals to 0. And therefore, that enables me to substitute into the minimization function. And after substituting the constraints and the objective function, I got this final function over here. And therefore, this marks the non-constraint function. So the first step is to find the gradient. So I found the gradient, and then I substituted the value of p equals to 1, and I got this long formula. After simplifying it, I went to here. And then I take the alpha to be 0.25 and the x and y values initially to be 0 and 0. And therefore, I computed my gradient, and I got -8 and -8. And then the x1 and y1, I got 2 and 2 upon substituting. So the initial was 0, 0, and then the alpha is 0.25, and then the R0, I got it through the calculation. So my x and y1 is 2 and 2. And then continuing further, I got the gradient. Next gradient is this, and then the B0 is this. And then I calculate the next R1, and therefore I could obtain the second x and y. Second x and y is same as the previous xy, which is x1, y1, minus alpha, which is a constant always, and then times the latest R1, which is over here. So I got x2 and y2. And here I noticed that from x1 and y1 to be 2 and 2, it went too far back to -576. And I just wanted to do one more iteration to confirm that, is this some sort of absurd thing? So I calculated the next gradient. I got this. The B1, I got that. And for the R2, I just used the same formula, substitution, I got this. And finally, the third iteration, I got x3 and y3 to be so big. I got 1.86 times 10 power 16 over, and then the y to be 1.86 times 10 power 16 also. And this was very weird because this function is very volatile. It's just exploding rapidly. And therefore, I had to resort to other ways to confirm whether it actually has a feasible solution or not. And that's when I just sketched the graph of the constraint. So for the first constraint, x squared plus y squared less than equals 15, it's actually a circle. And since both of them have to be positive, this graph is only on the positive side. So this dotted line marks the equation x squared plus y squared equals to 15, and the shaded area of purple color marks the shaded region for this inequality. And on the other hand, this line over here, the pink dotted line represents the value x plus y equals 8, and the shaded area on top represents the region for the x plus y more than equals 8, which is our second constraint. As you can see, the both constraints did not overlap each other, indicating there's no feasible solution which satisfies all the constraints. And therefore, I ended this question with a note that there are no feasible point that exists for this question. And lastly, I went to question number 3, which is a question that involves a minimization problem. And this equation is a multivariate equation involving 3 variables, x, y, and also z. And same thing again, I use the 4 last digits of a metric number. So upon substituting, I get this function over here, 8x minus 1 square plus 4y minus 2 square plus 7z minus 3 square plus 8xy plus yz. So x represents the traffic flow, y represents the fuel consumption, and z determines the terrain difficulty. So since I was allowed to use any suitable technique from the table 1 and table 2, I choose to use the Newton method. So the first step in Newton method, we calculate the gradient, and I did so over here. So the gradient with respect to x, with respect to y, and with respect to z is over here. And therefore, I equated to 0 all of them to find the stationary points. But as I can see here, this is not easy to calculate the stationary point, so I just left it like that and went to calculate the Hessian matrix. So since this is a 3-dimensional equation, the Hessian matrix is 3 by 3. So I have to calculate the second order derivatives for the x, y, and also z. So here are all of the entries that I calculated. And upon substituting into the 3-dimensional Hessian matrix, I got this Hessian matrix. And for the inverse Hessian matrix, I got this over here. And after that, I calculated the iteration number 1 for x1, y1, and z1. So the new x, y, and z is equal to the old x, y, and z minus the inverse Hessian matrix times the gradient. So the gradient, I got negative 16, negative 16, negative 42 upon substituting the value 0, 0, and 0 into this equation over here. And after that, I calculated the multiplication of Hessian matrix's inverse with the gradient. I got this, and therefore I could calculate my x1, y1, and z1. So I got my x1, y1, z1 to be negative 13, 28, and negative 13. So I moved on to calculate x2, y2, and z2. So to calculate x2, y2, and z2, I need to know the gradient of x1, y1, and z1, because that's the only thing that is continuously changing upon the iterations. So when I calculate the gradient for the x1, y1, z1, I got it to be 0. So after substituting into the equation, I got the old x, which is the x1, y1, z1, plus the multiplication of the inverse Hessian times the gradient, I got 0. So I got the same x values back again. And I went to the next gradient, I got still 0, and the x3, y3, and z3 to be the same x and y. So therefore, this method has converged to one singular point, which is negative 13, 28, and negative 13. So to confirm it's a minimum point, I used the Hessian matrix format. So I got the first order to be 16 more than 0. Second order, which is the 2 by 2 Hessian matrix, still the determinant is more than 0. But for the third degree Hessian matrix, I got the determinant to be negative. So this clearly indicates that this is not a local minimum, but it's in fact a saddle point. So I try to use different starting points to find whether it converges to a different answer. But then after using x to be 1, 1, 1, and 4, 4, 4, it always converges to negative 13, 28, and negative 13. And therefore, I ended my answer by saying that this is the converging point using the Newton method. And that's all from me. Thank you so much.